To graph a piecewise defined function, I've mapped out the following 4 steps, and all of these steps will fill in the blanks here, but they always make more sense once we actually do an example. So once you actually see the examples, I think these will be a little more clear. But these will be handy for you guys to go back to and refer to in your notes when you're working your homework. Okay, so the first step, we want to determine the left and right boundaries of each piece. And we know that the x values of each piece are given in the equation. And we also want to note that some pieces may have no boundaries. If they have an infinite boundary, such as x greater than or equal to 1, that would go from 1 to infinity. So some pieces may have no boundaries, but that's important to note as well. Okay, step 2. Once we find the boundaries, we want to determine the ordered pair that corresponds to each boundary if possible. And we'll do that by making an xy table, plugging in an x value, and then getting out your y value to make your ordered pair. If the boundary is not included, so that would be indicated with a greater than or a less than symbol without the equals, then that point, that boundary is actually going to be a hole, and we'll talk about that. We would indicate that with an open circle. Step 3, we want to determine any intercepts. So x and y intercepts. So x-intercepts, we could have multiple intercepts, x-intercepts. So each piece, no matter how many pieces the function has, each piece could actually have its own x-intercepts. So there could definitely be multiple x-intercepts. We know from our previous algebra courses to algebraically find x-intercepts from an equation, we're going to plug in a y value of 0 and solve. So we need to remember to test, because these are piecewise defined functions, we have to test each piece, plug in a y value of 0 for each piece to see if there's an intercept in the domain of that piece. Then to find the y-intercept, and we know that functions can have only one y-intercept, the domain tells you where the x value equals 0. So we won't algebraically to find a y-intercept, we plug in an x value of 0. So it'll tell us in the domain exactly which piece contains an x value of 0, if any. Then finally, we have enough information. We have boundaries, intercepts, potentially holes on those boundaries. And we'll use the equation, the shape of the equation, so we know if it's an x squared function, it's going to be a parabola. We know if it's a square root function, it'll be that ray shape, that ramp-looking shape. If it's an x cubed graph, it'll be that snake-looking shape. If it's an absolute value, it'd be the v, etc. So we have to remember those shapes, but then we just plot the points that we just found above and connect them with that appropriate shape. And then we want to remember that we want to use an arrow to indicate if a piece has no boundary. So if the piece goes infinitely x greater than or equal to 1, for instance, we want to put an arrow on that graph on the end of it to show that it goes infinitely to the right. And we'll show you that in some examples here now.